So it's time to start our final part of morning session. So our next speaker is Lucero.
Yes.
Yeah, Lucero. So from Arizona State, and she's going to talking about communication dynamics of a dyad
Yeah.
interaction model with applications to human automation teaming.
Yes.
So
thank you so much for the introduction. Thank you for organizing this and inviting me over for this wonderful workshop. Happy birthday, Gail. I'm really glad to be here and be part of this small conference. Okay. So what characterizes a good team? Well, one can say that the team must be able to achieve a lot more than the individuals will be able to achieve on their own. And this can only happen if the team is able to coordinate among themselves. So this is an idea that comes from Jamie Gorman from 2014. And they relate this to a lot with Aristotle quote, the whole is greater than the sum of its parts. So what's team coordination? So we know a team are two or more interdependent individuals that interact with each other to reach a common goal. And coordination is a dynamic arrangement of parts to achieve a larger task. And well, coordination is something that we use in our daily lives as an individual and when we're working, of course, with others. So I found these three different definitions of team coordination among the literature, and you're welcome to read them, but I want to point out that they have at least these two common points. So, and that is that it's a group of people that work interdependently, and they work to achieve a common goal. And the last one has a new key component, which is the flow of information. So these are some of the examples of team with coordination, and these are mostly the ones that are studied in human factors and ergonomics field. We have cooking teams, surgical teams, military teams, and aviation teams. So we're likely to interact more with the cooking teams every time we go out for a restaurant, right? We like our food to be good and warm when we eat it. And so this team is in charge to achieve that goal. So this, I'm sorry for the lettering, the change. So these are the components of teamwork. So in human factors, they like to measure or study team coordination, but really what we see is the end result is the teamwork. And teamwork is built first on collaboration, and then collaboration comes from coordination. And at the base of it all, it's communication. And that can be verbal or non-verbal. As human beings and by evolution, we're really good at communicating information just by hand gestures or face expressions. So this is a part of this. To study communication is really hard to study the nonverbal component, especially when we look at teams like sports teams. If you watch a basketball game, the team has to make decisions in a split of a second, and they don't have time to communicate verbally communication across the field, but they may use hand gestures and this face expression to pass the ball or whichever move they're going to make next. So yeah, studies have shown that communication, clear and precise information, how the communication, clear and precise information among all team members provides team functioning and task completion. So how can we study communication dynamics? So we can look at what factors of communication will benefit or harm the team, how these factors impact differently to teams with different levels of performance, and what characteristics are present in a high-performing team. So to model this communication dynamics, we'll take the modeling approach that John Gottman did in 2003 in his book. He has a book called The Dynamics of Marriage. It's pretty interesting. So he tries to model in the communication dynamics of a wife and a husband, and in there, he puts two components in it. So that is first the uninfluenced behavior of the wife and the uninfluenced behavior of the husband. And the second component is the influenced behavior that the husband has on the wife and the influenced behavior that the wife has on the husband. So we're going to start our single agent and mathematical model. So we're going to use a recursive model to do this as a discrete time. And the reason to do this is because communication, it's a turn-taking dynamic. So for example, here, Kevin. So we're going to describe Kevin. It's described by you. The communication of Kevin is described by you. R here, we're going to describe it as the emotional inertia. And emotional inertia just means, so if you have a high emotional inertia, that means that you're not that affected by your environment or other psychological events. So you're less likely to change your emotion according to those factors in the environment. So if you have in the system, if the person has high emotional inertia, that means it's a smaller R1 value. Instead, for a low emotional inertia, that means your emotion changes with the demands of the environment. It will change more easily. So that means a higher R value. And then K1 will be, it just means the mean communication level. So how fast can you talk, or how many words you're able to communicate in a certain period of time. So these are the assumptions for the two-agent model. So we have agent X and agent Y. Agent X has first an interaction A, and then to agent Y, and then agent Y has an interaction B to agent X. So that's how it goes. So it's, as I said, the communication is turn-taking dynamic, so it will be conveyed as a discrete time. The leader of the team initiates the interaction. The communication style of each agent without interferences from the other agent follows a recursive map. So that's the uninfluenced behavior. And then the influenced behavior is going to be of holding type 2. So this is how the two-agent mathematical model looks. Of course, we're going to have initial conditions. And I just denote the terms taken by X and Y. Just going to go here. This is the same model. So to explain the second part of the model, the influence term. So we now have Kevin and Sarah in the team. They're put in a team. Yeah. And so our beta parameters here will mean the nonlinear impacts that the previous, for example here, the nonlinear impacts that Sarah has on Kevin. And then the gammas here would be the damping effect, so his own regulation to those impacts of the communication from Sarah. And the same terms have it's present for Sarah, and that's of course with respect to Kevin's communication. So these are the model parameters for the model. All of them are going to be positive, with exception of the betas, can be positive or negative. So of course the model has the three boundary equilibriums, and they always exist, and they're locally asymptotically stable given these conditions. So for the first one, only let's say just only communication of Kevin exists in the team. So he has to have a high emotional inertia, and then Sarah has to Sarah's it's more heavily impacted by the communication of Kevin. And of course, if this R2, so that's the emotional inertia of Sarah, then of course this can be easily condition can easily be met. So then that means of course Kevin is gonna dominate the conversation. Sarah won't be able to speak. So to study the interior equilibrium, we first went and looked at the symmetric model. So we reduced the number of parameters from 8 to 4. And we trace the node clients to see the possible number of equilibria that we're going to get. So for the symmetric model, there could only be 5, 3, or 1 interior equilibrium. From the 5 of them, we could only explicitly describe these 2 that we see on the screen. And then to find the conditions for the existence of these equilibrium points, we use, we use the asymptotes of these node clients. So MATLAB could only trace the vertical ones, but these horizontal node clients can have either 1 or 2 here asymptotes. So we use those asymptotes as conditions to where it will, they will intersect the other node clients. So these conditions that you see here are built on those node clients. So we went back to the general model that you saw previously, and it changes a little bit the dynamics in the sense that this general model can have 2 equilibrium points, but it cannot have 2 and 1 equilibrium points. It's only 5, 3, or 2, or 5, 3, or 1. So yeah, we build those using these conditions to be able to identify when those intersections are going to happen. And then the 2 equilibrium points will happen only when this beta yx is less or equal than this quantity. So that's when we're going to happen the 2 points. Okay, so how can we really apply this model? Well, let's go to Kevin and Sarah. Kevin and Sarah were put into a team. So we're going to identify Sarah as the internal agent and then Kevin as an external agent of the team. And they have to work together to complete one task. And the task is to locate victims in an environment that has been attacked, had a terrorist attack, let's say. So Sarah is in charge to navigate the environment only. And she needs to find these victims, which are going to be green boxes. And she has to be careful of the red boxes, which means they're threats. And she has to click on the boxes on this environment to be able to rescue them. And if she clicks on the wrong boxes, she loses points for the team. She also has to also find blue boxes, which has to be done in a certain period of time because they're time sensitive. So Kevin is the external agent. So Kevin is in charge to guide Sarah through the environment. And to do that, he has a map of that environment, which is going to be an office. And he's also able to see what Sarah is doing and see everything that Sarah is also looking at. But the model contains, the map contains inconsistencies with the environment. So they're forced to be in constant communication to determine where to go next and which places, which rooms they have already visited. So Kevin is also in charge to mark the rooms in the map to check where Sarah has been and if it's a clear room. So this is actually a experiment that was done in ASU in 2015. So this is how the data set looks. So we do have which agent spoke, the time lag, which is how many times passed between one communication to another, the number of words, and then at the end, I was able to calculate the number of words divided by time lag. The reason why we have operator and robot was because during the experiment, they told, let's say, Kevin that Sarah is a robot. So, but it's in reality a human. So I'm just assuming everyone's a human here. So the study classified teams. They gave a performance of the team. So we have rooms marked correctly, which is Kevin's in charge of, correct presses on the boxes, repeated presses, and incorrect presses deducted points from the team. So I did a classification of low, medium, and high performing teams with this scores here. So we have 10 teams for low performing, 21 teams and mid performing, and 9 teams as a high performing team. So we have, I did a general fit-in, but I also focus in fitting the model with assuming that both agents have an overall same personality, to see if two persons are very similar in their personalities, what will be the parameters that we have to fit related to their the betas and the gammas. So in the sense of the team being put as these two persons being put as a team to complete a common task, saying that the parameters beta and gamma are going to be related to their training, because the way they respond to questions and information is going to be related to how do they know what to do next. Okay, so we have the 3 types of teams. If you pay close attention to the data, which is the black dots, the difference between low, medium, and high is that, for example, high, there's a lot of communication between agent X and agent Y, and it's almost similar. The density is almost similar. And then for mid performing, that also have we also have similar density, but the Y agent might be a little bit less, but what the resemblance happens more between low and high, when agent Y has speaks very little compared to agent X. So that's how the teams differ in each other when we saw the data like this. So we did some bifurcation diagrams to see first what will happen, the stability for the interior equilibria, and when are the 5 equilibrium points are going to appear as we vary one parameter. Here we're able to see this is the boundary equilibrium. So the top and the bottom are the boundary, and anything in the middle, of course, is the interior equilibrium. So sometimes I'm going to show low and high performing teams together. Sometimes I'm just going to show the high performing. So for this, I fixed the parameter k to equal to 5. So in this first simulation, I chose an R, a low value for R, so that's 1.44. So that means a high emotional inertia. So in this simulation, what I want to show is that the first interaction is essential for two agents with high emotional inertia, and that can be because maybe both agents are at the beginning can fight for their initial leadership, and if one is overpowering the other one, then the other one will stop talking. So yeah, so the initial interaction is essential in this case. So now we looked at the damping effect from agent Y. So we fixed the R's and the K's. So for here, we look at two simulations for high performance. So we decrease the gamma parameter, and we see that by decreasing, it decreases the variability of the communication of agent X. And we don't want this scenario. And the reason of that is because if one agent is all over the place communicating a lot of information, and in a sense gets freaking out about what to do next, then if agent X has very static communication, then agent X will not be able to lead the way, or in a sense calm down agent Y to be able to navigate the environment and complete the task. So again, we did not fit in, but in this time we say, okay, let's say both agents had the exact same training, and that means both agents were trained for their own tasks, and they were trained for the tasks of the other agent. So they both know exactly what to expect from the other. So again, bifurcation diagrams to see, and we vary just R1. Let's see what happens if we change the emotional range of the leader, which is going to be agent X. So if we introduce an agent that has very high emotional inertia, then we're going to get this dynamic for agent X. And again, as mentioned before, we really don't want to have one agent behaving this way, very static, and the other very chaotic. So and then we looked at what's going to happen if we change how their communication affect each other, so the betas. So for this, if we increase the betas, this is quite interesting. There was no effect on the communication, but I'm thinking that we got this result because if we look back here and the fitted parameters, so they both have low emotional inertia, but they have a pretty good damping effect. And then since both are affected, let's go back. If they're both affected equally, then that's why we had this like pretty stable effect on both agents. Yeah. So the conclusion for this study is that high-performing teams, we need two agents, one with constant communication, The external dyad, which is going to, again, the agent X needs to take the leadership of the team. The teams that display poor communication or sporadic communication from either of the agents were not able to perform well and obtain low scores as a team. And this is from this data. So if we look at agents with the same personality, then if we have two agents with high emotional inertia, then the quality of that first interaction among them, it's important, regardless if they're low or high performing team. And if we're decreasing the damping effect of, here's agent X, then this results in a change in the variability on the agent X, and then agent Y will take the leadership in the communication. So agent Y is going to populate that communication. And then if we give them both the same training for their task, if we put agent X with high emotional inertia, then again, agent Y is going to populate that communication among the team. And if we decrease the nonlinear communication effect, so the beta parameter, the high-performing teams, in the high-performing teams, then the initial interaction between the agents will not affect that future communication in the team. So, of course, the model has quite a few limitations. So we don't take account the workload that both agents have. We don't consider the trust they have among them, and we don't consider the quality of the information being passed, and we don't have the performance across time from the data. So, but what if we could actually introduce a completely autonomous robot that is able to complete one of the tasks of one of the agents? So this is actually work that ASU does in unison with the US Army. And they describe robot as a device or a system that could partially or completely perform a task that is done by a human. So right now, as we have the technology, the communication between robots and humans is done by the human giving orders to the robot, and the robot performs the task. A simple example of that is your phone, right? You can ask it to create an event in your calendar, and it will do it for you. But some robots are being given important tests. So the experiment design was actually done to mirror the urban search and rescue teams. So that's one of the situations that the robots are using in real life. And of course, the agencies that are really interested in this type of research is the US Army, NASA, and Air Force, that they're using robots and systems to complete tasks to increase the security of their agents. And yeah. So right now, we actually, in addition with our collaborators, we're working on another experiment from the US Army, the interaction between you as a driver, and then how you use the automation from your car, the cruise control. And they put the automation system, you could have just the speed control, or have the speed control and lane centering capability. So we call it full automation. And it's a simulated experiment, and the driver has to go through these cars, and they has to follow a vehicle. And during this simulation, they have certain perturbations, like pedestrians walking right in front of your car, or wind gust that takes you out of the lane, change of speeds, So we're looking at how the operators interact with the automation with different types and levels of performance of the automation. What drives the operator to trust and rely on the automation, even though it has the automation has some difficulties performing the task. And the really big question is, can we estimate the level of trust and decision making from this data and looking at the behaviors of humans like in this setting? So these are some of collaborators. Carlos is another PhD student who I'm working with. Dr. Kang, of course. Dr. Cook and Dr. Chu are from Human Factors. Dr. Metcalfe is from the US Army, and Dr. Amisin is from the Department of Psychology. Yeah, so some knowledge. Again, thank you for inviting me to the workshop and the support to come here. Thank you.